Yeah. Let's start. Good afternoon, everyone. So this is fifth day and the last day of our workshop, and we'll be doing today combinatorics or counting techniques. I'll just mention the names. You may not understand each and everything right now, but whenever you learn later, you'll understand what are these things. So, like you count in a smart way, or you don't count actually each and everything. So many times this is called as counting without counting. Mhm. And there are various techniques. So, for example, basic principles are addition and multiplication principle. Addition and multiplication principle. Then, as counting with sets is concerned, we learn inclusion exclusion principle, which is very useful in inclusion exclusion principle. Then there is well-known principle called as pigeonhole principle. So shortly it is called as PHP, pigeonhole principle. That's again something simple and interesting. So there are various such ideas in counting, and that forms this subject combinatorics. A good book to start with is, I don't know, any simple book at your level, but I suggest one or two books. So one book particularly dedicated to combinatorics is following Principles and Techniques in Combinatorics. Principles and Techniques in Combinatorics. By there are two Chinese authors. One is Chen Chuan Chong and the other is Ho Ki Meng. So Chong and Meng. These are the Chinese names. Another book which I have already said on first day, which is very useful in general for your uh, growth of analytical skills, logic, etc. Mathematical circles. So that contains a lot of such techniques and chapters. Mathematical circles. This was told on first day.
Thank you, sir.
So we'll start with puzzle type of problems and we'll see some problems from combinatorics which without much introduction we can try today. Yeah, shall I go ahead? Let me just check the chat box. Please don't write unnecessary things in chat box like hi, hello, this, that, and so on. Only answers. Whenever I ask, only answers. Is that fine?
Yeah.
Yeah.
Hello, sir.
Yes. 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 Okay. So this is session 5 of our workshop. This is last day, and as promised, we are doing combinatorics. So 5 days we did one puzzle, first day puzzle and introduction. Then four topics of any Olympiad or maths competition like number theory, then geometry, then algebra, and today combinatorics. So let's start with puzzle type of problem. Yeah. So here you say, suppose you draw that structure in your notebook carefully. So first what you can draw is that outer equilateral triangle. Divide each side into four equal parts and join those points as you can see here. And you see there are some smaller triangles. So the question is, count the number of triangles of all sizes. Count the number of triangles.
So can I just look at it from here and like do it without a notebook?
It's better you draw that diagram because question should be with you.
Sir, don't you post like the questions like on the classroom?
Yeah, this all will be go in your classroom.
Yes, sir. I can just like print it out afterwards if I need it.
Yeah, okay. Count the number of triangles of all sizes. Of all sizes. Yeah, and the idea is, in fact, you count it systematically, then you'll get correct answers. That's the idea of combinatorics. Okay, as usual, I'll give some time. Once you get answer, you can put it in chat box only to me, not for everyone. Don't disclose the answers. Don't write unnecessary things in chat box. Only answers. Is that fine? And what I was saying. Viraj, don't rush to the answers. Count it properly. Count it very carefully. You have to count the triangles of all sizes. Please don't rush to the answer. This is Olympiad, not some race like I'm getting first, I'm getting second, and so on. So count it very systematically. I'll say something. You count in two cases. So one case where your triangle has a vertex upwards, this type of triangle, and different sizes like size 1, size 2, size 3, size 4 is the original triangle. Okay, and count triangles which have vertex downwards. So do you see there are both types of triangles, vertex upwards and vertex downwards. For example, this is vertex downwards. Is that right? This is vertex downwards.
We have
Yeah.
to count like the whole triangle or the triangles only on its sides.
Triangles, number of triangles.
Oh, okay, thank you.
Yeah. So there are this type of triangles of various sizes, and there are these type of triangles vertex upwards. These type of triangles vertex upwards, and of different sizes, size 1, size 2, size 3, size 4. So count systematically and you will get the answer.
So I have sent you my answer.
Sir, I sent it to you before
In
anyways.
fact,
Like,
even I don't know exact answer. We will count together later.
so I sent it to you.
Yeah, okay. We'll work together and you can check whether you are correct or wrong. Okay. Vertex upwards, these type of triangles. Okay. And size 1. How many are size 1? So like for example, this one, 1, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you see,
Sir, I think you're counting it wrong.
Sir, I got 16.
Yeah, so there are 16 small triangles, sir. You're not
no,
counting the
no,
ones.
no, 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 I'm counting only with vertex upwards, not all of them.
Oh, sir.
You are counting all type of triangles. This type of triangle as well as this type of triangle.
So, sir, you're going to count that later, like separately.
Yes.
Okay.
I'm counting only those which have vertex upwards. So with size 1, there are see exactly 1 plus 2 plus 3 plus 4. And in fact, such numbers are called as triangular numbers. You can represent them using triangle 1 plus 2 plus 3 plus 4. So they are called as triangular numbers. This turns out to be 10 together. So fourth triangular number is 10. Fourth triangular number is 10. So what is that? With size 1, there are 10 triangles. Okay?
And downside vertex 6.
Uh, no, still we have to count other sizes. Size 2, size 3, size 4. Size 4 is the original triangle, right? Now, size, which color I should use? Blue. Yeah, size 2. What are size 2? For example, this is size 2. Do you get it?
Yes, sir.
1. You move little down and you see again there are two triangles of size 2. Okay, again you move one level down and you see there are three triangles of size 2. So again it's essentially triangular number 1 plus 2 plus 3. 1 plus 2 plus 3. Yeah. So size 2 there will be 6 triangles 1 plus 2 plus 3. Size 3. Size 3. I hope now everyone has got idea. Size 3 vertex upwards. and there are 1 plus 2, 3 triangles. 1 plus 2, 3 triangles. Is that good?
Yes, sir.
Yeah. And size 4, the actual triangle, vertex upwards, right? So size 4, there is one triangle. And
The whole triangle.
check these are all triangular numbers. 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So this number is 20, right? This is 20. And this is one type of triangles, that is vertex upwards. Still we have to count vertex downward triangles. So they will be of this form. And use thick lines. Size 1. Size 1. 1, 2, 3. So 1 plus 2 plus 3, right? Again, they are triangular numbers. 1 plus 2 plus 3. That is size 1. 1 plus 2 plus 3, that is 6. Size 2. Size 2. Where do you see size 2? Size 2 is this one. This one, right? How many are there? Size 2?
1.
Only one. Check. Only one. Right? So size 2 there is 1. And that's it. There is no size 3, no size 4. Size 3 and 4. 3 and 4, nil. 0. So total there are 7 vertex downwards. Vertex downwards. And see that we have divided the problem into two separate parts. One, triangles of vertex upwards, other triangles are of vertex downwards, right? And what do you think now? What is the answer? Total answer, total count?
So 27.
20 plus 7, right? So this is called as addition principle. This is called as addition principle. Or let me explain with a simple example. Like suppose in your class now, there will be some grade 6 students, some grade 7 students. Suppose there are 10 grade 6 students and suppose there are 15 grade 7 students. Together we have how many in the class? 10 plus 15, 25. That is addition principle. Is that good? So by addition principle we have 20 plus 7. That is 27 triangles. That is the answer. Okay, everyone is convinced. Now check your answers. Whether right or wrong. Yeah, good.
I got 25.
Yes, somewhere you must have counted less. You must have missed some case, some case. Okay. Yeah, Viraj has raised hand. Viraj,
So, you know the big triangle?
huh.
Think the four size threes.
Big triangle has size 4 and vertex upwards. So that we have counted here.
No, I think actually the big triangle has four size threes. Because, like, I can see one here, and one here, and then one more on top of them.
Okay. Size 3 you are saying Just a
Yeah.
minute. Just a minute. I'll draw them uh, with thick lines. Okay, so start with this vertex. This is 1, right? This is 1. Then you come one level down, like this one. Go shift right side, this one. So 1 plus 2, 3. Now I can't go down. That won't give me triangle of size 3. So 1 plus 2 only. Okay?
Okay, so I'm convinced, sir.
Yeah. And for all of you, I'll say it again. You at your leisure later on work on all these problems, and that will help you more. Yeah. Shall I go ahead? Any doubt?
No,
Okay.
no, sir.
So let's go ahead. So this is one principle, addition principle. You divide the problem into some parts which are totally independent of each other, totally separate. They don't have any common cases. And then simply you have to add these cases plus these cases. That is addition principle. Okay. So let's go ahead. I'll shift it and make it bigger. Yeah. Can you see the problem, all of you? There are 3 cities A, B, and C. There are 3 different paths from A to B. Let's say, suppose we can go from A to B via, say, for example, air, rail, and maybe say road. And from B to C, we can go via 2 different ways. Maybe road and maybe say water, like by boat or something, right? Now, if I want to go from A to C via B, A to C via B, in how many different ways I can go? I'll explain what I mean by different ways. Like for example, suppose I go from A to B first by road and then again by road. That is one way. And suppose if I go from A to B
So
by
6 ways.
road, if I go from A to B from by road and then from B to C by water, that is different way. This is taken as different way. Okay? Please don't disclose the answers. Keep it with yourself. You can raise your hand whenever we want to discuss. You can explain what are your explanation. Okay? Yeah. So I have explained what are different ways. Then in how many different ways I can go from A to C via B. Via B. Maybe it's a small number of cases. So you can actually write down all possible ways and count it that way. Okay, I'll wait for some time and then you can explain what are your logic and we'll see the actual answer. Yeah, combinatorics is more, I mean, these counting problems are more like a puzzle. And I see there are many answers today. I'm happy.
Sir, one question, like from A to B, like if we do like rail, then you go back to air, then you go to road, and then first you go to road. Is that possible?
Oh, no, no. So we have to go from A to B. Don't go back. A to B and B to C then.
So, sir, there's no going backwards.
Yeah, yeah.
Okay.
So very ideal cases. Like why we should go again from B to A?
Sir, I
Sir,
forgot
if you
something
get
at
lost,
home.
then
Sir, I forgot something at home.
Yeah. Okay. Raise your hands and one by one I'll come to each one. Atharva, your hand is raised first. Atharva. And next is Anaya. Atharva.
Yes. So let's consider that there are five pathways. Like
Huh?
the pathways from A to B are 1, 2, 3, and to B and C there's 4 and 5.
Okay.
First, we will use first path to go to A, then fifth path to go to C. That means one way. Then 2 to 5 another way. Then 3 and 5 another way. Then we use 4. 1 to 4 another way. 2 to 4 another way. 3 to 4 another way. So that means in total there are 6 ways.
Okay. Yeah. So you what's your answer? Atharva's answer is 6.
6 ways.
Okay. Yeah. Okay. And uh, listen to your logic also. Yeah. Good. Anaya. Ananya. What's your name? Sorry.
Sir, Anaya.
Anaya. Yeah.
Sir, so there are 6 ways from A to B. We can go, and then from B, like from A to B air, and then B to C water. That's one way. Then A to B rail, and B to C water, and A to B road, and B to C water. So like we do that till water, and then we go on road. Then we do A to B air and B to C road. Then A to B rail and B to C road, and A to B road and B to C road.
Okay. Yeah. Then who else wants to say? Just a minute. Viraj.
So I really didn't get the same answer because I got confused because like it says how many different ways can one go from A to C? I thought from A to C there were only two because like there's road and water at the end. That's what I thought. Like
Yeah. So yeah, that's a good question. So when I say road from A to B and road from B to C, they'll be taken as two different things, right? Because I mean cities are different. So obviously, in between, what are Cincinnati or what are shops, what are malls, uh, what are number plates, etc. They'll be all different. So A to B road and B to C road are two different things. Yeah, that's a good question. Good point. Okay. So I'll try to explain my logic. Like I can make pairs. For example, A to B air. I go via air from A to B, and from B to C there is no aerial way, and I go either by road or by water. So that gives me two different ways. So air, road, air, water. Is that fine? So these are two different ways. Then similarly, I can go from A to B by rail first, and then again I have two choices: railroad, rail water. And similarly for road, so I go from A to B by road. I have two choices. I'll continue with road again from B to C. I'll go via water from B to C. So For each choice here from A to B, there are two choices here from B to C. And how many choices are there from A to B? There are three choices. And for each of them, there are two choices from B to C. Okay? Now, do you see this is not addition principle? For each way from A to B, I can attach two different ways from or two different choices from B to C. So it will be essentially multiplication. So that will be 3 into 2. Is that good? So 3 into 2.
Sir,
There are
it's a
six,
logic type question.
yeah, six different ways. And essentially this is called as multiplication principle of counting. So when do we use multiplication and when do we use addition? So when there are two independent cases of the problem, you count case 1, you count case 2, and you add all of them. That is addition principle. And there are two cases like A to B, B to C. But for every case here, for every choice here, there are, or let me say in terms of variables, suppose there are X choices from A to B, and for each choice from A to B, there are Y choices from B to C. Okay, then how many total choices I'll get, how many different ways I'll get? X into Y. So for example, in this case, 3 into 2, six different ways. What six different ways? Air road, air water, railroad, rail water, road, road water. So there are six ways. This is called as multiplication principle. Okay, all of you. Still, I see some raise hands. If you are already done with, you can lower your hand, please.
So this is like one of those logic questions that come in Olympiads.
Yes, yes. And by practice, it will be very clear to you like when to use addition principle, when to use multiplication principle. Sometimes there is even mixture of both principles. So you divide it into cases. Case 1, you have to use multiplication principle. Case 2, you have to use multiplication principle, and then add all those answers. So sometimes it's a mixture of both principles. At least these are some basic simple problems, puzzle like problems, and they are totally different or disjoint problems. In this problem, we have to use only multiplication. In first puzzle, we have to use only addition principle. Yeah, good.
So, but we can also use addition principle. Like we first add the air ones, then the rail ones, then the road ones.
Hmm. Yeah. In fact, in some sense, multiplication is repeated addition. So you may call it in that sense addition principle. That is fine. But see the point that for every choice from A to B, I have two choices from B to C. Right? So I have to multiply by number of choices from A to B by number of choices from B to C. That's the idea. Right? Okay. Shall we go ahead? Now stop writing in chat box, please. Shall we go ahead?
Yes, sir.
Yeah, if this problem is clear to everyone, I'll make it little complicated, little complicated. So suppose from A to B, there are three different ways. From B to C, there are two different ways. And from C to D, there are again three different ways. Okay, in how many ways we can go from A to D via B and C? No returning back. Don't forget anything at home. Only one way journey. A to D. Only one way. You can't go back. I see some non-mathematical comments there. They're interesting,
A to
Sir, I don't understand
but
the
don't.
question.
Okay, okay. Yeah, I'll explain again. Do you understand this first question before this?
Yes, sir.
Yeah. Now I've made it little complicated. Instead of 3 cities, there are 4 cities, A, B, C, D. There are 3 different ways to go from A to B. There are 2 different ways to go from B to C. That part is same as first part, first problem. Now from city C to D, again there are 3 different modes. In how many different ways I can go from A to D?
Oh, okay.
But I have to take B and C. I can't go directly from A to D via some air or water or something. I have to take in between B as well as C. What are the different ways? Please don't write unnecessary things. Write only answers. Focus here.
send to the answer.
Okay, okay. Yeah, so I will say something. Is it again multiplication principle? All of you agree?
Yes, sir.
Yeah. And only thing in this case, it's multiplication of 3 numbers. 3 into 2 into 3. Is that good?
Yes, sir.
Yeah. So the number of ways is 18. 3 into 2 into 3. Answer is 18. Check your answers. I hope everyone must have
Done,
got this.
sir.
So same logic applies even for 3 cities, 4 cities, or you make any n number of cities. You have to keep on multiplying. For every choice from A to B, there are 2 choices from B to C, and for every choice from A to C, there are 3 choices for C to D. So in all, I have to multiply all these cases, and that gives me 3 into 2 into 3. Again, 18 is a small number. If you want, you can write uh, with some names. Like for example, I can call this as road 1, road 2, road 3, and call this as path 1, path 2. I can call this as way 1, way 2, way 3. And I can write each path from A to D as a sequence like R1, P1, W1, R1, P1, W2, R1, P1, W3.
So
So for
basically, the trick for this question is to just multiply the number of
yeah,
ways.
yes. So for each and every path from A to C, I have 3 different ways from C to D, right? And how many paths are there from A to C, which already we have counted 3 into 2, right? So in all, what you get is 6. Earlier answer into for every such case, I have 3 choices from C to D. So 6 into 3, that is 18. Is that good? Okay, shall we go ahead?
Yes, sir.
Yeah. Again, one more puzzle type of problem. I'll explain first and then you count.
Sir, one more thing. Whenever I open the Google Classroom for this to, see the problems which come in the like A4 size paper size thing, so it does not load. It all that loads is your notes which you're taking.
I don't understand what was the problem.
So, like there are problem sheets which you add differently to this paper, and then you solve it like previously how you did for A, B, and C. So
Mhm.
it does not load on the Google Classroom notes sheet. Or all that loads is what you are writing in your markup.
Oh, is that so? Okay, okay.
Yeah.
Okay. I'll ask the admin team. So I don't know about those technical things. I just send this whatever whole of this as a PDF. So from my side, it goes as a whole PDF, everything. Whatever I write, whatever I have type, everything. So I don't know. That must be some Google problem.
Okay.
Yeah, I'll ask them. Okay.
Yeah.
Okay. So next one, I'll make it bigger. I'll first explain. Don't rush to the answers. It's a simple looking problem, but it's not as obvious as it looks like. Okay. So you see that diagram, and you have to start at point A. You have to start at point A. There are 4 petals for that upper flower, and there are 3 petals for that lower one. If you want, you can call that point as B. So how many different ways you can draw it? So I'll explain. There are 4 petals. I can number them 1, 2, 3, 4, and I can first draw maybe this petal. Later on, I'll draw this one. Later on, I'll draw this one. I'll draw this one. I'll come back again to A. I'll come down. Okay, again there are 3 petals. It's my choice whether to draw right one, lower one, left one. So I'll draw right one, then left one, and then lower one, and then left one. So, so this I can do in various different ways, right? Like for
So you
example, I
forgot
can.
the stem of the downer flower.
Uh-huh.
You forgot the stem of the flower below.
Yes, yes. Yeah. So for example, I can number these as 1, 2, 3, 4. I can number these as 1, 2, 3, 4. I'll trace any of those first. Maybe I have traced first 1, then I have traced 2,
Sir, I sent you my answer.
and again that I can
Sir, I
do in
sent you my
different
answer.
ways. Just a minute, listen to this. So I can do it in 2 different ways. I can draw it this way, clockwise, or I can draw with opposite orientation, anti-clockwise. So each petal I can draw in with 2 orientations, clockwise or anti-clockwise, and I can have different choices of drawing those petals. Maybe here I am drawing petal 1 first, then petal 2, then petal 4, and then petal 3. Right?
Sir, I
So,
have a doubt.
so that is one way. Right? Again, so my ordering will be different for petals 1, 2, 3, 4, and that will be different way. So you have to count in how many different ways I can draw this given diagram. Is the question clear to everyone?
Sir, can we move on to the bottom part without completing the upper part?
But
That is also a possibility.
yeah, but see that there is some condition without lifting the pen and without retracing the portion. So if you want uh, uh, if you want to come you have to come from A to B, right? And if you have not completed upper part, you have to trace this part again.
Sir, can I explain my answer?
That is not permissible, right?
Sir, can
Atharva?
I sir, can I give my answer?
Wait.
Okay.
Yeah, Atharva, is that clear? So you have to start at A, draw all 4 petals, come down, and then draw 3 petals. You can't go back again via same road, via this road. If you have not completed upper structure, you have to go back. You have to trace again on this path. Oh, sorry. Where is my cursor? Yeah, I have to go back again. right? And that is not allowed to travel along this path to and fro.
Understood, sir.
Sir, I texted you the answer.
Okay,
Me too, sir.
wait for some. In fact, answer is a very big number. So you see, simple looking figure you can draw in so many different ways.
So the Garshan sent the answer to everyone.
That must be by mistake, I guess. But let me tell you again and again. For Olympiads, never look at ready-made solutions or other solutions. Do try on your own, right? So if somebody by mistake, suppose post answer for everyone, you do simply ignore. Don't look at it. Yeah. Divit wanted to explain the answer. First, tell me what's your answer, Divit.
Sir, before I thought it was 48, then I changed my answer to 128 because I gotten confused.
Yeah.
So sir, each petal has two lines where you can start from. So sir, like 2 times 2 times 2 times 2 times 2 times 2 times 2. So 2 to the power of 7, which is 128.
Okay.
But sir, I have a feeling it could be higher, but I'm not
Yes.
sure.
Yeah. It's much higher.
Oh, okay.
Yeah.
So let me try again.
But but still, I mean, part of your logic was correct. Like every petal has two choices. Either I can draw it clockwise, or I can draw it anti-clockwise. I can draw. Look at here. I can draw every petal this way, or I can draw it this way.
Okay, sir.
Right? And same I can do for each and every pattern. I have 2 into 2 into 2 into 2. It's multiplication principle. There are 7 patterns, so that will give me 2 raised to 7. That's fine. That's good. Okay. But
From
let
each petal, you can go to 3 others.
yeah. So let me talk about these petals. I'll number them. So maybe 1, 2, 3, and 4. And you see, I can draw any of these petals first. Right? Any of this. From A, I can draw this way. So I'll draw fourth. Or from A, I can go it this way. So I'll draw one first. Or from A, I can draw this way. So I'm drawing two first. Or from A, I can draw it this way. So for first drawing first petal, I have four choices. So petal one, drawing petal one, first petal. I have four choices. All of you agree? Any of these, one, two, three, four. Any of these.
Yes.
Suppose I have drawn, say for example, left one, petal number one. Now, for the drawing second petal, I have three choices. I can draw either this one, or I can draw this one, or I can draw this one. I have three choices, right? So for petal 2, drawings petal 2, I have three choices. Is that good? Those raise hand, please lower down your hands. Okay, is this good, all of you? Petal 1, I can draw any of those four petals. I have four choices. Either I can do it this way, or I can do it this way, or I can do it this way, or I can do it this way. Is that good? Once I draw first petal, for drawing second petal, I have three choices now because one petal is already exhausted. I draw. So suppose, for example, I have drawn this one. I have drawn this one. Okay, now there are three petals left, and I have three choices. I can draw any of them first. So for drawing second petal, I have three choices. Is that good? Then for drawing petal 3, how many choices I have?
Two, sir.
Everyone agrees? 2. And for last petal, I have only one choice, the left petal. What are left?
But sir, there are still three petals at the bottom.
Yes, yes. So I'm talking first about this part. We'll divide the problem into two parts. First count upper part, then count lower part, and for every upper drawing, I have every possible lower drawing. So it's upper into lower. It's multiplication principle, and for each part again there is multiplication principle. So I can draw those four petals in 4 into 3 into 2 into 1. This is called as 4 factorial. So this number shortly is denoted by this notation, exclamation mark after 4. What it means is 1 into 2 into 3 into 4. 5 factorial is 1 into 2 into 3 into 4 into 5. Or more generally, n factorial is 1 into 2 into 3 into 4 into so on up to n. So this is called as factorial. Factorial. And it's very commonly used symbol in combinatorics. Factorial. So 4 factor, 24. And into, as David said, every petal I have two choices. I can draw it this way or I can draw it this way. Is that good? So 24 into two choices for each petal. So 2 into 2 into 2 into 2. That is for the upper part. Upper part. Count this number and tell me what is this. 24 into 16.
384, sir.
384. All of you agree with this? 384. Okay, one more point. One more point. Nowadays, we have computers, calculators, everything available. But make it a point whenever you want some calculation, do it manually. Don't use some machines like calculators or maybe laptops or whatever. Okay, so always make it a habit to do calculations manually because in Olympiads we are not allowed any machine, any computer, calculator, anything.
Sir, for when I'm not doing Olympiads, I made this code that can calculate factorial of a number.
Oh, very good. Yeah,
So like I just use that instead.
yeah, yeah. So you see, in fact, just after 9, 10, the number goes too high, too big, right? And uh, there are some programs. I don't know. I'm not good at computers. I do only mathematics. But there are some techniques which calculate big factorials like 100 factorial and so on, which is practically, I mean, difficult to write even on paper. And there are some programs, some techniques which calculate that factorial in parts. So even you can compute some big factors like 50 factorial, 100 factorial, and so on with programming. Okay, so try to learn those techniques. Yeah, don't write in chat box now. Please focus here. So 384 is answer for the upper part. All of you agree? You can draw that upper petal, upper flower in 384 different ways. Now see, simple flower with 4 petals, and you can draw it in 384 different ways, right? So if, for example, if there are 384 students in a school, everyone can draw in different manner. No two ways will be same.
Sir, one petal has four ways. No, sorry, three ways.
No, each petal you can draw in two ways, either clockwise or anti-clockwise. Orientations will be, there will be two orientations opposite to each other. But order in which you can draw those 4 petals, that turns out to be 24. I can draw any of them as my first petal. So I have 4 choices. Then I can draw any of those remaining 3 as my second petal. So I have 3 choices. Then for next petal I have 2 choices. And for the last one, obvious one choice. So it's 4 into 3 into 2 into 1. 4 factorial, that is 24 choices. So 24 into orientations of each petal, 2 into 2 into 2 into 2. So there are 384 ways. For example, see, suppose in very obvious way, I start with petal 1 and I go clockwise, petal 2 clockwise, petal 3 clockwise, petal 4 clockwise. This is one way. Now some student may draw it this way: petal 1 anti-clockwise, petal 2 anti-clockwise, petal 3 anti-clockwise, petal 4 anti-clockwise. This is totally different way. Each petal are drawn in opposite fashion. So my way and his way are different, though orders are same. Is that good? So that counts the upper part. Now all of you count similarly lower part and put it in chat box. Then we'll go ahead. Count number of ways for drawing lower part and see that you can't keep upper part incomplete and come down, because you can't go back again to A. There is no retracing. So I have to complete upper flower, go to that base A, come down. I'll call this point as B if you want. Come to B, and from B draw 3 petals. That's the only way. Draw first upper part, then draw lower part. So now count number of ways to draw lower part. Do it correctly if you have understood upper part. And let me tell again and again, don't rush to the answers. Okay, in Olympiads we have a lot of time. It's like, it's not a 100-meter race, it's a marathon.
So what are
What
we
do you
doing now?
huh?
What are we doing now?
No, you people do it first, and then I'll explain further. So count number of ways for drawing lower part. For upper part, there are 384 ways. Okay, I'll suggest all of you, if somebody writes something other than answers in chat box, please don't respond. Once you respond to that, the chat starts. Okay, and your focus goes from lecture to that what are writing in chats. Don't respond to anyone.
So 48 times.
Wait. Okay, so I want now answers in chat box for the lower part. Keep writing only answers, and only to me, not for everyone. More answers, more answers. I want more answers. Then we'll start further.
How many answers did you get, sir?
Wait, wait. Let people put some answers and then we'll continue. Okay? In fact, if you understood properly the logic for the upper part on same lines, you can work for the lower part. So there are three petals, and which means I can draw just those three petals in three factorial ways. That is, I have three choices for the drawing first petal, then two choices for drawing second petal, and one choice for the last petal. So it's 3 factorial, and for each petal again I have two orientations. So into 2 into 2 into 2. Is that good? So that is 6 into 8, 48. So that is answer for lower. And again answer for the whole thing will be 384 into 48. Calculate this number and put it in chat box. 384 into 48.
Sir, I've sent it to you.
384 into 48. Ataro, it
Sir,
will be
are
huge.
there 10 ways?
It will be huge number. 384 into 48. And so only one correct answer. Are you doing or not? If possible, you can on your videos. Let me check who are doing and who are not. Okay.
Sir, done.
Have you put in chat box? Yeah.
So my video doesn't seem to be working. It's on, but like,
Okay. Okay. Yeah. Okay. So check your answers. Answer is 18432. 18432.
yes, sir, 18 for 32.
And see that
Yes.
it's such a simple diagram. 4 petals upper side, 3 petals downside. Without retracing, right, and without lifting the pane, you can draw it in how many different ways? 18,432. It's too much, right? Yeah, so that is about second answer, and it again uses multiplication principle. Is that good? All fine so far. Shall we go ahead?
Sir, how did you use the multiplication principle?
For each part, we have used multiplication. What is factorial? It's multiplication, and again into 2 into 2 into 2 into 2. So that is all multiplication, right? and even for lower part, it's multiplication. And for drawing one case on upper side, have 48 different cases on lower side. So it's again 384 into 48. So that again is multiplication principle. So everything is multiplication. Okay. Shall we go ahead? Can you see the problem? Third one. How many integers between 1 and 100? You have to take into account both numbers 1 as well as 100 are, now there are 5 different questions. We'll answer one by one. How many of them are divisible by 2? Separate question, how many of them are divisible by 3? Separate question, how many of them are divisible by both 2 as well as 3? Fourth question, read carefully, look at the wording. Fourth question, how many of them are divisible either by 2 or by 3? At least one of them. So question 3 is 2 and 3. Question 4 is 2 or 3. And question 5 divisible by none of 2 and 3. Okay. Please put answers to all 5 one by one.
So can I ask a
Only to,
question?
just a minute. Only to me. Don't reveal it for everyone. Please. And don't write unnecessary things in chat box.
So sent you the answer for the first.
Okay.
So can I ask a question?
Sir,
Rajesh,
won't
sorry.
sir
Yeah.
won't the third
Anyone?
sir won't the third one actually just be divisible by 6?
Yeah, divisible by 2, both 2 and 3. So that
Yes,
will be,
sir.
yeah.
So when you say like divisible by either 2 or 3, do you look at the one that is divisible by 2 and 3 as well?
So for example, suppose if I give you number 4, is it divisible by 2 or 3?
Yes.
Yeah. So because it's divisible by one of them, not both of them. Okay.
So
But
like 6 cannot come into that category.
even 6 can come. 6 also will come. It's
Okay.
divisible by one of, at least one of them. At least one of them. So if you are lucky, it's divisible by both of them. That is
So,
fine.
so for question 4, when it says divisible by either 2 or 3, does that mean all divisible? Does that count all divisible by both 2 or just separately?
Yeah, yeah. So divisible by either one of them or both of them. See, generally in our day-to-day usage of language, English language, like for example, suppose if I tell some of you, if it is, I'll come to your home or I may not come. Then
Okay,
I
so
can do, I
no,
can do
so it's
only
so
one of
it's
them.
sir, so
I
it's
can do
sir,
only one of them, right?
sir. That means that divisible by either 2 or 3 means question 1 plus question 2 minus question 3.
That will say. That will say. Okay. So yeah, so this is called as when it is exclusive or only exactly one of them. That is called as XOR, and mathematical OR is inclusive OR. So what we take is inclusive OR, either by 2 or by 3 or by both. It's inclusive
Oh, okay, sir.
or by both. But when I say 2 and 3, it's by both.
Sir, I've sent you all the answers.
Okay. Yeah, we'll see one by one.
So the meaning of 3 and 4 is basically the same then.
No, no, no. So, like for example, suppose if I give you number 4, that won't be valid here. Like it's not divisible by both 2 and 3. So in problem 3, you'll get numbers like 6, 12, 18 divisible by both 2 as well as 3. And in case of 4, it's either by one of them, so multiples of 2 or multiples of 3, or those which are multiples of both. Okay?
Yes.
Yeah, I want some more answers. Then we can start with the discussion.
So I've sent all my answers to you.
Yes, yes, I saw that. Shall I start?
So can I explain my answers?
Better I'll explain because now
Okay.
time is less and this is something new. So maybe I like to explain myself. Okay? Just for this problem. Is that good?
Okay.
So out of 1 to 100 divisible by 2, that means which are multiples of 2. That is 2 into 1, 2 into 2, 2 into 3. Like this I can go how far? 2 into 50, that is 100. Right? So how many numbers are there?
15.
50. 50. And how can I do that as far as computation is concerned? So numbers divisible by 2 are 100 by 2.
100
Now,
divided by
yeah. Now luckily in this case 100 is completely divisible by 2. So I get whole number 50. But see that same logic when I work for 3, 100 by 3 is not integer. There will be some remainder. So I get quotient 33 and remainder 1.
Yeah.
Okay. So I take integer part that is denoted by bracket, integer part of 100 by 3 and that is 33. Because your answer number of integers divided by 3, it can't be 33.333, right? So it will be some integer. All of you agree? So it should be integer part of my division or quotient part of my division. So that is denoted by bracket 100 by 3, 33. So even here also I'll write bracket 100 by 2. Luckily it is integer. So I don't have to take integer part. Already it's integer. So answer to first one is 50. Then answer to second one is 33. Okay. Now, I'll express with some diagram. Such a thing is called as Venn diagram. So you express the set in terms of some circles, squares, etc. That's called as Venn diagram.
Yes, sir, I've seen that in Olympiad.
Yeah, yeah.
Yeah, so Venn
So,
diagrams.
so those numbers which are divisible by 2, I'll put in one box or one circle. So like 2, 4, 6, 8, and so on. Those which are divisible by 3. And are there some common things divisible by 2 as well as by 3?
Yeah, like multiples of 6.
Yeah. So multiples of 6 will be common. So 3, 6 is common. It's in both sets, multiples of 2 as well as multiples of 3. Right? Then next will be 12. 9 will be here. 12. 15 will be here. 18 and so on. So all even multiples of 3 will be common. They will be divisible by 2, divisible by 3. Right? So when I say divisible by both 2 and 3, it is basically what? So third answer is 100 by 6. They are multiples of 6. Right? And what is that? Again, integer part. Only integer part.
Yeah, it'll be 16 and a remainder of 4.
60. Okay? Forget the remainder. That will give me fraction. So it's basically 16 numbers. And what numbers? 6 into 1, 6 into 2, 6 into 3, up to 6 into 16, which is 96. Next multiple is above 100. 6 into 17 is 102. That is above 100. So we won't consider that. There are 16 numbers which are divisible by 6.
Then the answer 4 is 83.
Let's see, let's see. So answer 4. Now take care. Like when I
No,
count,
so it's 67.
let's count. So divisible by either 2 or 3. That means either by 2 or by 3 or both. Right? Okay. Now see that all these numbers are here. Divisible by 2, divisible by 3, and some are in fact common. So see that like numbers like 6, 12, 18, you have to count only once, right? But you count when you count multiples of 2, they get counted once, and when you count multiples of 3, they get counted again one more time. So multiples of 6
You have to
get
minus.
counted twice. I have to count everything only once. Are you following, all of you?
Yeah.
Yeah. So what I have to do is post answer. So I'm saying answer for fourth. Post answer 50 multiples of 2 or divisible by 2 plus divisible by 3 and
Minus.
maybe both, right? But both I have counted at two places, once here, once here. So I have to subtract it once. This is called as inclusion exclusion principle. Inclusion exclusion principle. So you add it, and if you are over counting, you subtract it, exclude it. Inclusion exclusion principle. Okay. So 50 plus 13 minus 60. Why minus? Because multiples of 16 I have counted twice, once in multiples of 2, once in multiples of 3. So I have to subtract it once. And that gives me 83 minus 16. 83 minus 16. How much is that?
67.
67. 67.
So I thought you said that divisible by either 2 or 3 or by both would be a 50 like plus 33.
Huh.
Your first two answers.
Yeah, why I have to subtract something? See, like those were numbers which are divisible by both. So numbers like 6, 12, 18, etc. I have counted once in that number 50, multiples of
Okay,
2.
sir. Okay, sir.
And I have counted also once, one more times in counting multiples of 3.
Okay, sir. Then I'll just change my
Yes, so as far as
question to.
Venn diagram is concerned, you see that block is in fact common to both of them. So I counted twice. When I count multiples of 2, when I count multiples of 2, I count this part, I count this part, and when I count multiples of 3, I count this part. So I counted twice. And what is counting? Like suppose, for example, if you have 10 friends standing together, and if you count, you have to count every person exactly once. That is counting. Counting is one for each object, one for each person. So I have to count these numbers 6, 12, 18 only once, exactly once. But I count them twice, once here and once here. So I have to subtract one once because I have counted twice. So that is called as inclusion exclusion principle. Okay. So that is 67. Now divisible by none of 2 and 3.
Is
Neither
that
by 2 nor by 3.
is that to do 100 minus 67?
Yeah. So that is, do you agree? It's exactly complementary case of this. Either by 2 or by 3. Neither by 2 nor by 3. They are exactly complementary cases. So fourth, fifth answer is 100 minus 67. That is 33. Yeah. But of course, in actual course, we'll be doing a lot of practice of such problems. So don't worry if in this first go you have not understood each and everything as far as this problem is concerned, right? I wanted to just give you idea of what is combinatorics. And so I selected these problems. Yeah, okay. So I'll summarize the things and then we'll conclude. Wait for some time. Okay, so this was a 5-day workshop, which was a teaser workshop for our course FMOTP, Foundation Maths Olympiad Training Program. At RAM, we have 3 different levels of Olympiad programs. One is for grade 6, 7, or maybe some good students from 4, 5th standard. Then next is for 8th standard and so on. IMOTP, Intermediate Maths Olympiad Training Program. It's not IMO, it's not International Maths Olympiad. Intermediate Maths Olympiad Training Program, which is usually students of 8 onwards or those who want to appear for the post level IOQM and RMO, etc. And the advanced level AMOTP, Advanced Maths Olympiad Training Program, which is usually 9th onwards or those who get selected for IOQM RMO. So this is basically INMO level. I'd say RMO INMO level. So for all of you, this was like teaser program for FMOTP, like how we conduct our sessions, what topics we teach, what is our methodology, etc. So you'll get to know all these things through this Spider workshop. As well as this Spider workshop, what you can do is go through all those PDFs once again, right? Twice, thrice, read it twice, thrice, solve all problems on your own, write your notes, and that will be good preparation for any maths competition like uh, NMTC, BMTSC, JMO, SASMO, AMC 8, and so on. So whatever we have done in these 5 days, that will also be very useful for all these maths competitions, which you can appear in 6, 7. Okay, now as far as actual course is concerned, our FMOTP course is divided into 3 convenient modules. So FMOTP runs in 3 modules. Each module runs over 2.5 months. Each module. So it starts from usually June. All those posters, links, etc. will be sent to your groups, right? And I hope all of you have enjoyed this 5-day workshop. So if you like this, math, if you find this challenging as well as interesting, if you have enjoyed this workshop, then you can think of joining our FMOTP course, which is in 3 parts. Okay, so you don't have to do it for whole 1 year. Whatever module you want, there are 3 independent modules. As per your convenience, you can join those modules. But I mean, if you are serious about Olympiads, my suggestion you join right from first module. So that is usually conducted on twice a week, Monday, Tuesday. It's twice a week, Monday, Tuesday, 7 p.m. to 8:30 p.m. 7 p.m. to 8:30 p.m. Okay, so that is about this workshop. I'm sure all of you have enjoyed this. You can on your videos and you can just give a thumbs up if you have enjoyed this or if you have liked this.
So my video isn't working, so
Okay. Bye then. Okay, bye then. Thank you.
bye, sir.
Yeah.
Bye, sir.
What is sir our start date on
Uh-huh.
mm, next asking about what I'm not seeing your photos of what we are doing in here to my father.
Oh, Shreyas, I told your case to our admin team. They are going to look after that. I told
Okay,
them with your name that you are not getting, you are
okay,
getting some
sir.
problem getting those PDFs and so on. Okay. So
Sir.
they'll look after that. Okay.
Okay, sir.
Yeah.
Thank you, sir. Bye, sir. Thank you, sir.
Yeah. Bye everyone. Thank you.
Bye. Bye, sir.
Bye.
Bye, bye, sir.